Okay, so continuing on with step 7, then let's enforce these boundary conditions. We're trying to solve for the constants. So we have our temperature function there. So what do? We're going to take our function, which is now the sum over I of Ci cosh of lambda I h times sine of lambda I x. And we need to multiply that by the eigenfunction, which is just the sine function again. So that's now times sine of lambda I x. And then on the right-hand side, we still have to keep in mind that this is a boundary condition we're enforcing. So on the right-hand side, we had th. So this is th over here. To keep the equation equal, we have to multiply the right-hand side by the eigenfunction as well. So sine lambda I x. So we haven't changed the function other than to multiply both sides by sine. To use orthogonality, though, we have to integrate. So we're going to take this thing now, and we're going to integrate the part that's a function of x. So let's see. So let's drop this integral in here from 0 to w, and then this is with respect to dx. And then over here, we have 0 to w with respect to dx. So now you can kind of see where this is going, I think. We're trying to get rid of x, right? That's the whole point of this. We need to get rid of x in these functions so that we can solve for Ci. If we do a definite integral on the x function, x goes away, right? You end up with an integrated value here. We have lambda times h, that's not functionally dependent. Now we're going to be able to solve for the Ci's. That's where this is going. Okay, so let's look at then what? Let's see. Yeah, let's think a little bit about the orthogonality example. Well, you know what? I think we've covered it for the most part there. So let me just show you how this is actually solved. One more step here. Yeah, so let's just simplify this down a little bit just to get our final expression. So, okay, we have this for every single value I, or a summation for every single value I. It's important to realize that this equation is true for independently for each value of I. Right, so we're taking the summation of all this. Each independent index I, this relationship also has to hold. So we can write this expression as a single function, Ci cosh lambda I h. This is the integral from x equals 0 to w of sine squared lambda I x dx is equal to integral 0 to w th sine lambda I x dx. Let's make sure I have all that right. Yeah, so this is true. So once we do this integral, again, we're going to get the constant. So let's look at how you actually do that. So we'll go to the next slide so we get ready for that. And I'll just show you on Maple how this works. Okay, so in Maple, what we're trying to do is take the individual integrals that we have. Right? On the left-hand side, we have sine squared of lambda. On the right-hand side, we have just the integral of sine. But we need to integrate these knowing that lambda is something specific. Lambda is its own function, or there's an evaluation for lambda. So the way that we're going to do this is we're going to use Maple to help us evaluate these integrals. It's not that they're super hard, but it's just a good thing to know how to do. So first, to note, in Maple, you can use this command called int, which obviously gives you the integral. So if you just say, I'm going to integrate some function, here I've got x squared, you give it the variable that you're integrating with respect to, it'll do that. And it's an indefinite integral. If you want to do a definite integral, the nomenclature is similar, except you give it the bounds. So you'd say x equals bound, low bound, dot, dot, upper bound. And when we do that, should evaluate and then give you back a numerical value, assuming everything else is defined. OK, so that's like the way you do the integration. What we need to do is program in these lambda functions. So lambda, if you remember, some lambda I is going to be pi times 2i minus 1 over 2w. That was from early last lecture. What we want is to prove that if I have some lambda index I and I have another lambda index j, that these follow the properties of orthogonality. So we can do that. I'm going to say lambda I is this function, but I need to tell it that I is something special. So I is an integer. So we're going to assume I is an integer, assume j is an integer, get these two expressions. Again, noting that like I and j have that little tilde that shows up because we've specified something about them. And then we're going to take the integral. So this is the integral on the left-hand side, that sine squared. I just want to prove, again, symbolically, that if I take the integral and I is not equal to j, that this is 0. So let's do that, and it is. Right? It just works out that way, even symbolically. Now, if I have a case where I equals j, that's just sine squared. Right? So that's this function. So that's really what we're trying to evaluate now. And it turns out, when I evaluate that function on the left-hand side for this particular lambda, as it's defined, I get w over 2. So now that whole integral goes away, the whole functional dependence on x goes away, and I can just plug in w over 2. Same thing on the right-hand side. Let's just integrate sine of lambda. So on the right-hand side, I'm going to have 2w over pi 2i minus 1. So we can go back and look at how this plays out. So let's see, what did we just do? Let me write it down. We said I have c I cosh lambda I h times the integral of 0 to w sine squared lambda I x dx is equal to th on the right-hand side, integral 0 to w sine lambda I x dx. So we just evaluated this and decided this thing over here is just w over 2. And this thing over here is, what, 2 minus 2w over, see, I can't remember, I can't even see. Was it minus? I don't think it was minus. 2w over pi times 2i minus 1. OK. So now I can actually solve for ci, right? Give me some index I. I can solve explicitly for ci. And I can compute the value of that constant. Right? And that's kind of the core of it. So let's do that. Ci is equal to 4th divided by pi times 2i minus 1 times cosh lambda I w. Right? We know what lambda I is. We know what I, we'll just assume any I, so now we can compute our constant. And we're basically done. So now we just say our full temperature is equal to the summation over all I of Ci cosh lambda I y times sine lambda I x, right? Where this Ci here just plugs in to that value. And that's it, right? Yeah?
Shouldn't that lambda I w be a lambda I h?
Did I do it wrong? Let's see. Where am I? Lambda I. You mean in the constants?
Yeah, the constant for Ci.
Yeah, it's possible. I messed it up. Lambda I. Yes, thank you. Yeah, right, because cosh is going to be applied in the y direction, so you wouldn't want w to show up in that function. Okay, so there's like kind of this long, drawn-out process, but in the end, you get this really cool result, I think. You've taken a problem that is in 2 dimensions. You've said, I'm going to solve this problem using sines and cosines and adding them up. Multiply all that by some other function, and you can actually model the temperature profile for this type of problem. So is this something, it kind of brings up that question, like, you sit here and you think, am I ever going to use this? I don't know. I mean, maybe you will. But like, you have these tools that you're building, right? The first thing you want to do is say, can I model this as a resistance? Okay, there's some assumption that you can't model as resistance. Can I then model it as a 1D solution? Maybe, maybe not. You just keep going and you check off these boxes of, increasing complexity. And at some point you might get to a problem like this where you say, okay, my domain is roughly rectangular, and I have these relatively simple looking boundary conditions. I can analytically build this model, and then you don't always have to run off to ANSYS or whatever like sledgehammer tool that solves every possible problem. You can be a little bit more elegant, and you could solve difficult problems like optimization problems that require a lot of evaluation very, very quickly. Right? You don't have to do a FEA heat transfer model for every single thing that you're going to do in your career. Right?